speaker of this session will be Hummels, telling us about resolution and process.
Thanks, Phil. Yeah, so I'm Cameron. I've listed a number of my collaborators here on the different projects that I'm going to be discussing, from the Trident synthetic absorption line spectral code, the collaborators within the CGM community of the fire simulations, and then the Tempest simulations, and attempt at doing this with grid-based codes. All right, so since I'm the first talk in the CGM session, I'm going to really quickly just give a quick overview of CGM so all of the other speakers in this session don't have to. And then talk a little bit about how we can compare observations of the CGM against the simulations that we have, and then finally talk about the meat of this this talk. Does resolution actually matter in the course of trying to resolve some of the problems of simulations of the CGM? So, what do we know about the CGM and why do we care? In my cartoon here, the CGM, the circumgalactic medium, is just a low-density gas that surrounds all galaxies. It's fed externally from the IGM through cold flows and hot accretion. It's also fed internally by AGN feedback, supernovae feedback, AGB stars, and so on and so forth. So really, it's probing a lot of different mechanisms, physical mechanisms associated with galaxy evolution. But more importantly, the reservoir of gas in the CGM, all the gas that eventually makes it into a galaxy that forms stars has to pass through the circumgalactic medium at some point. So it's crucial to understand this phase of gas for understanding the total galaxy evolution for all of the galaxies that we have in the universe. The observations of the CGM are really challenging because you can't see, it's so low density, you can't see it in emission. So we rely on background objects like quasars with well-characterized spectra going through the circumgalactic medium, getting absorption line features and such from that gas that show up in your resulting spectra. These are typically UV resonance lines for certain ionization transitions like neutral hydrogen, magnesium 2, carbon 4, oxygen 6, and so on and so forth. And what's interesting about this is it can reveal a huge amount of information about the phase of the gas along these different sight lines. Here's just a phase plot showing temperature and density for an old ENSO galaxy simulation that I had, and I've drawn on top the several approximate locations of several different ionization transitions and the phase of the gas that's being probed by these transitions. So as you can see, we're able to learn a huge amount of information about the metallicity and the phase of the gas from looking at several of the presence of several of these lines. But because these are individual sight lines, it's problematic. You can't resolve all of this structure for a single galaxy unless you have something like MUSE or KCWI, which I'm sure we'll hear about later. But we have to rely on these different sight lines, and that's problematic. You have to put these together. Observers have to put these together into these, typically done in radial profiles, where you have impact parameter on the x-axis and either equivalent width or some characterization of the strength of these columns of ions on the y-axis, and stack sight lines from several different observational sources, assuming spherical symmetry with your galaxies. And essentially what you see is the strength of ions is highest in the center of the galaxies, and it drops off as you go farther out in the galaxies. So this is what observers provide us with, and when simulators try and reproduce this, we generally fail. Nobody in the field has self-consistently gotten matching the observational data sets, all the observational data sets with a single set of simulations. And usually what happens is these radial profiles undercut the observational sample, seen here or here. So what we really need to do in terms of simulations is bulk up the total amount of column densities that we're seeing in our simulations to try and reproduce those found by observations. Okay, so I think that's enough of an intro. Why do we care? All accreted gas in a galaxy has to come through the CGM. CGM observations possess a huge amount of information about the phase of the galaxy, and simulations are basically unable to reproduce the CGM observations. There's a lot of tension there. So very quickly, I'm going to touch on how we can compare simulations and observations of the CGM. Essentially, what we're trying to do is take a simulated data set and put it into this radial profile that we get from observations. One way we can do this is by forward modeling this data, sending sightlines through our simulation, and producing something like the observations. And that's exactly what we do with this code called Trident that I released in the last 6 months with collaborators Britton Smith and Devin Sylvia. This is an open source Python-based code that anyone can download and use. It's going to be used for the Agora simulation CGM comparison project. And essentially, it does a variety of things. It's built on top of YT, so it supports basically all astrophysical hydrodynamics codes in the field. You can run it on your data set, no matter what code you're using to simulate things. And it allows you to post-process data sets to incorporate ion fraction fields that you didn't necessarily have by making some assumptions about collisional and photoionization in your simulations. But I won't go into too much on this, but I encourage you guys to use this. And then this is just a demonstration of kind of how it's working. This is a slice of data through a simulation showing density, gas density here. And as this sightline travels through these different clumps of gas, I just picked silicon-2 as an example ion here. It's going through silicon-2 bearing gas. And so as it does so, it creates absorption line. We deposit Voigt profiles for each of the gas elements bearing silicon-2 at the appropriate Doppler redshift as well as cosmological redshift, and you can get something like this out. Okay, so go to trident-project.org and download the code if you want. It's pip installable. It's pretty straightforward. Okay, so now the real thing that I wanted to talk about, does resolution matter in simulating the circumgalactic medium? So to address this, let's talk about resolution. When I talk about resolution, traditionally resolution is tied to the dense structures in your simulations, whether that's intrinsically in particle-based codes where your spatial resolution is tied to the inner particle distance. And so in regions of high density, you'll have more particles there. And so your inner particle distance is lower, so you have higher spatial resolution. Or this could be done explicitly in the case of grid-based codes using AMR. So usually the refinement criterion that people choose to use is based on density. So you will intrinsically have more resolution in regions of high density than you will in low density. This is problematic because it means that low density structures like those in the circumgalactic medium, which is low density, could be under-resolved. And under-resolving gas tends to be unphysical. So imagine, for instance, you have a small clump of gas, cold gas, right next to a larger envelope of hot gas. Multi-phase gas, that's all fine and good. But if your gas resolution element encompasses both of those structures simultaneously, you wash out that structure and you combine those into an unphysical warm medium, which is not going to be reflective of what's actually going on in that gas. And can give you, I'm going to claim that this is much of the reason that our simulations of the CGM are unable to reproduce observations, because we're not resolving that multi-phase structure, and we're just doing a poor job at physically modeling it. So as an example of this, here's a face-on view of a galaxy. This galaxy here, with the virial radius marked shaded. Here's an edge-on view, and in a traditional AMR run, this shows the spatial resolution that we're able to achieve. You find higher resolution around the disk of the galaxy, but out in the halo near the virial radius, that resolution can drop by a factor of 10, 20, 30, something like that, relative to the resolution that you're quoting for your simulation. So collaborators of mine and myself are running some simulations called the Tempest simulations, where we force higher resolution in the halo in order to avoid these problems. And it still allows AMR due to density in case there are density structures that come in, but we're forcing resolution in the outskirts. And these Tempest simulations are run using the ENSO code, and we're claiming better than 1 kiloparsec spatial resolution out to 100 kiloparsecs proper in the halo. So as an example of this, I have a movie showing 2 runs, one with, they're both exactly the same simulation, starting with the same initial conditions. This is with standard traditional AMR, and this is where we force the resolution. And if we run it forward, we'll just run it forward. We're looking at column density of H1 here. And what you see is in traditional AMR, we're lacking a lot of the structures that you now see in this column density map of H1 that are allowed to collapse, because essentially what's happening in these runs is, because you're having higher resolution, it allows multi-phase medium to form, and it allows cold gas to collapse, and H1 is sitting in this cold gas. And so you find significantly higher column densities of H1 in the circumgalactic medium when you actually allow it to resolve and fragment. Okay, so very quickly, does resolution matter? Yes, it's crucial. And in the case of the Tempest simulations, resolution enables a multi-phase gas, and you find higher column densities of both cold gas as well as very hot gas, and lower column densities of this warm medium. But in addition, I've been looking at the fire simulations, which of course many of you are familiar with, and essentially taking one of these simulations. This is a density map, and again using Trident to apply to show the H1 and the O6, but we do this for a variety of different ions. And as you can see, the H1 sits in the cold gas, typically at the centers of these galaxies, whereas the O6 is in a more extended halo, because the O6, the ionization potential for O6 is much higher, so it tends to sit in 10 to the 5th or 3 times 10 to the 5th Kelvin gas. So if we then make radial profiles like what the observers do from this sort of thing, you get these radial profiles where you've got impact parameter on the bottom, and then your column density for H1 and column density for O6 in these two plots. And what we've shown here are 3 separate runs of different resolution. The black line represents the radial profile for the lowest resolution, blue is medium resolution, and green is highest resolution. The green being the latte runs that Andrew Wetzel published in the last year or so. And I've overplot the COS halos data sets on top. And what you can see is as you increase the resolution, you're finding higher column density gas in your simulations. But what's odd is that even the oxygen 6, which is in much hotter gas, it's pretty well resolved in the simulation. So you wouldn't think that increasing the resolution would assist in increasing the column density of oxygen 6, but it very clearly does. So why is this? Oxygen 6, you can increase your oxygen 6 content by 2 things. You can either increase the total amount of oxygen and metals in the halo, which will increase your oxygen 6 content, or you can increase, you can bring the existing oxygen into the phase of gas where oxygen 6 tends to reside, which is about 10 to the 5th Kelvin. So what's actually happening? These are radial profiles for temperature and for mass-weighted temperature and mass-weighted metallicity. You can see, again, these are the 3 different resolution runs. The temperature doesn't change appreciably across the halo as you increase the resolution, but the metallicity distinctly does. And it's not that there are more metals in the halo. I mean, they're a little bit more, maybe a factor of 2 or less. But it's just that the metals are more well distributed in the halo. The higher resolution in these fire runs allows the metals to get out into the halo where they can be absorbers for the CGM sightlines. And we're still investigating what the mechanism for this is, but generally the way I like to think about it is that the smaller particle masses of metal-bearing gas that are kicked out of supernovae are able to travel into the halo more effectively because they require less acceleration from multiple contemporaneous supernovae that are going off, that are kicking them out there, than large massive particles, as is the case in low-resolution runs. So does resolution matter? Yes, it matters for 2 separate effects. One, it enables this collapse of gas into cold structures and hot structures, but it also allows more efficient distribution of the metals within the halo as a whole. And so if you take anything out of this talk, the one thing I want you to take out is increased resolution is necessary to bring up the column densities in our simulations to relieve some of the tension between CGM simulations and CGM observations. Thank you.